Okay, so let's start. Today I want to discuss about Floquet theory in quantum mechanics. So basically, I just write the title first. Floquet theory in quantum mechanics. So basically, it's kind of a generalization of a periodic perturbation theory, and so basically these types of problem appears in the physics or in the quantum mechanics because when we want to solve if the system drives in a periodic uh, time periodic potential or something. So if we drive a system periodically, so then the solution of the system will be appear corresponding a differential equation which is uh, periodic in its variable. So then we may set up some uh, problem and follow some theory, uh, and then we just find out the eigenvalue of the system. So first, I just wanted to state you and convince you that if a system is a Hamiltonian, which is a time-dependent Hamiltonian, and follows a symmetry, the periodic symmetry or the time periodic symmetry, that means that Hamiltonians is repeatedly comes back into the original Hamiltonian after a period of time t. So, and this t is basically driving frequency. So, inverse of the driving frequency. So, it's kind of omega d. So, 2 pi over omega t. So, and this omega d you can state that is a driving frequency. So, it's a driving frequency. So, what is the symmetry? It follows that it's a periodic symmetry. So, it's a time period symmetry. That means this system appears repetitively into this original form uh, at a period that is at the time t. So, this capital T. So, that's the main essence of this system and follows the symmetry, and the system appears repetitively. So that's the case. So you think of so basically what I say. So this is not a perturbative thing. So there is no perturbation in it. So it's a original Hamiltonian which has a periodic drive. So this system suffers from a periodic drive. So this T appears due to some you may call it's a periodic drive. Periodic drive. So it's not something like the time dependent perturbation theory. So it's not actually a time dependent perturbation theory. So it's a theory where the system uh, suffers from a periodic time or and follows a time periodic symmetry. So as an example, you can think of the simplest Hamiltonian you can think of as an example that if your Hamiltonian is kind of look like this, so maybe this sigma z cos omega t. So this is the drive frequency, so omega d maybe, and plus sigma x, and obviously the energy out of this. But so these sigmas are the Pauli matrices, and what it follows that this part is the periodic in time, and it has some periodic symmetry. So that's why you can think of the simplest possible cases that your Hamiltonian, which is time dependent Hamiltonian, so and there is no perturbation in it. So now we so as long it is, so I did not perturbatively expand also. So we will do that. So after a few minutes, so maybe. Okay, so the this equation follows a Schrodinger equation that uh, look like something I h bar del t of your wave function psi t and your Hamiltonian h of t with psi of t. So this is a set of Hamiltonian. So your uh, right hand side, that this portion of this equation, of this Schrodinger equation, which is the periodic of time, periodic in time, and your left hand side, which is the differentiating your wave function with that variable which is periodic in time. So which is the which follows the periodicity. So that's the thing. So basically you can also find out, or you can guess that your psi t should follow something psi of t plus t. So actually we don't know about the psi of t, so we have to solve to find out this psi of t. And so we basically see that this right hand portion, right hand side of this equation is a periodic in time, and this left hand side of the portion, which the variable which is differentiating your state, which follows the periodicity. So it follows a symmetry that original Hamiltonian does, which is the periodic in time. So the time periodic symmetry, it is followed. Okay, so historically this set of equation comes into the mathematics before the quantum mechanics came. So the scientist name may be Gustav Floquet, who did this. So historically he said, so so he said that if you have a equation, maybe x dot of a x, where x is your n column vector, and a of t, so basically this should be a of t is your n cross n matrix, and it is that it you may also think of that a of t plus t follows this symmetry, that a of t. So for this kind of this set of equation, you may find out the solution that x should be e to the power some mu of t p of t x0. So where this is the periodic function, if any periodic drive, if a system is driven by a periodic drive, then that system follows this kind of differential equation. And this method established by Gustav Floquet did in the context, not in the context of quantum mechanics, he did in the context of the solution of the differential equation, which suffers from a periodic symmetry, and this set of some equations. And he shows that the solution of this kind of equation, which structurally in this form, then in, uh, you can evidently see the solution of the equation should be in this structure. So this mu is the coefficient which we have to uh, find, because it's the unknown coefficient which we need to find to know this system. And this pt is the periodic functions appears in your solution, and the x0 is the maybe the amplitude, so basically the solution at the initial time. And as this class of equation follows this kind of periodic symmetry, so you can immediately think of that your x at t equal to 0 is basically 1, and as it is a something called p of t at t equal to 0 is equal to that this function at the t equal to capital T. So at this period, which should be equal to 1. So this class of uh, generalization I can make because the system follows the periodic symmetry. So that periodicity allows us to do this, uh, do this or write this kind of solution for this class of the differential equation. And what I so this the proof of this uh, equation I'm not going to discuss because it's a completely mathematical thing. If you are interested, you can check on the online sources, maybe in Wikipedia. There is a good, very good article on this, so you can check. So this kind of equation, the solution of this differential equation is. But immediately I can I can use into the quantum mechanics scenario. So where our system Hamiltonian is driven by a periodic symmetry, a periodic drive. So and follows some periodic symmetry. So okay. So next, what we do, so by taking the help of this Floquet theory or the Floquet solution, so by the taking the help of this Floquet solution, I can immediately see that our psi of t would be take a form like uh, minus I of mu t p of t psi of 0. So this is a state in the initial condition, and the psi of t something e to the power minus mu of t psi of 0, as your pt, this periodic function, is equal to 1 at t equal to 0 and the t equal to capital T at that period. And immediately you can name this mu in terms of minus I hf t over h bar psi of 0. So that's the thing. So I just name this mu in terms of hf over h bar, and this hf, so this hf would be your Floquet Hamiltonian of the system. Floquet Hamiltonian of the system. So that's it. And what I find from this kind of set of equation that uh, the the system follows this kind of periodic symmetry, that psi t, this psi t can be written as a time independent Hamiltonian, which depends on the uh, time, which depends on the time, which is periodically symmetric in nature. So I just write the statement here. So first I erase this. So what I found, that your state psi t can be written as time independent quantity which depends only on the drive frequency. So which depends only on the drive frequency. So what is the benefit of doing this kind of stuff? Because if you have some time independent thing like this Floquet Hamiltonian, which is the time independent one, so you can find out the energy eigenvalues from it by diagonalizing this Hamiltonian. So what we get from by solving the differential equation which follows the Schrodinger equation and also follows the periodic in time, or the system drives into a periodically driven system. So that kind of system we can came up with a time independent Hamiltonian, and we can find out the energy eigenvalues from this time independent Hamiltonian, which more or like same the uh, energy of the original Hamiltonian. So they are most likely the same. But that energy eigenvalue should known as the quasi-energy. Why it's quasi? So basically, in the time dependent theory, so people could not have any kind of energy eigenvalues, because actually in the time dependent system there are no kind of the time translation symmetry. So we couldn't find this kind of energy eigenvalue from the time dependent system. But if I manage to solve this kind of, or manage to impose that the periodically driven system in such a equation which basically follows the time periodicity or the variable periodicity, so then we can find out a coefficient which is independent of time, and our state which can be written as a function of a time independent quantity, but that system which should be dependent on the drive frequency only. So that's why we can it's a benefit to find out this kind of energy eigenvalue which is more likely the same of the original Hamiltonian. That's why we named these energy eigenvalues are the quasi-energy eigenvalues. So that's the whole scenario. So people would also think of about the Bloch theorem, because there are some periodic potentials. It depends on the space. So in that scenario, so as the system don't have some spatial symmetry or the spatial uh, uh, so so if the system suffers from a uh, periodic potential which is the periodic in space, but there are no kind of translation symmetry. So as there is no any translation symmetry, so people don't have any kind of momentum out there. So but in the Bloch theorem we labeled our uh, energies in the momentum space, and they are labeling with a k, and there is a k is find out and which quantized our system in terms of the space. So that's why that momentum uh, is basically a quasi momentum of the system. So that's why in the case of the Bloch theorem we find there is a spatial periodicity or the periodic potential are there, but we find some momentum which is the quasi momentum. And in this type of the system where the system suffers from the periodic drive in the time periodic drive and follows the time periodic symmetry, uh, that kind of system gives us the quasi-energy eigenvalues. That's it. So basically in this scenario, and it is very beneficiary to do this, because if in this scenario, to determine this kind of time evolution, if you know that t, if the t is basically some quantization of the periodicity, maybe 1t, 2t, 3t, so n belongs to your integer, so then if you know this kind of basically steps of the time, and how long you have to go in the time, because you just want to know about time evolution, and the and if you know the period, so that's enough to do or know the system, because you don't need to know other thing, you have to know this part. That's it. So another statement I just want to write, which is a very good statement, I guess, because as in the block theorem, momentum is not no longer be a good quantum number. So in this scenario, you find out the quantization of energy in terms of the quasi energies. So that's why. So if if there is periodicity, if there is a periodicity in given variable, that means here for our problem is the time, uh, in given variable, so its conjugate variable is almost conserved. So as I said that you find out, you can find the quasi energies. So that's why it is not the equal to the energy eigenvalues of the original, but it is almost equal to the energies of the original Hamiltonian. So that's why we can make a statement clearly that if the system suffers from a periodicity in a given variable, that means in this case that is a time, or maybe in case of the block theorem that should be a space, then that its conjugate variable, it's almost conserved. That means in case of the space, you could find out in the block theorem that is the quasi momentum, and in this case in the Floquet theory, for the time dependent problem, which is periodically driven, so this kind of system gives you some energy, that's the conjugate of the time, so that almost conserved. So that's the statement we can make, but it's almost not exactly conserved. But we can think of that the basically the property of the original Hamiltonian we studied. So that's the scenario of the Floquet theory. Okay, so now we just going to discuss about the dynamics of the system. So what to do, and it is very simple thing that you all know about the time evolution and all that. So as we know that our system is basically h of t plus capital T, and where t is basically 2 pi inverse of the drive frequency. So your psi t should follow the form that exponential of minus I hf capital T over h bar of your initial state would be there, that is psi 0. So in quantum dynamics, so what we do, so quantum in quantum dynamics, there should be a evolution operator, that your psi t should be evolved with some, you follow some unitarity, that psi of 0 and you can write this u of t comma 0 is something time ordered of minus I of h bar, so 0 to t h of t prime dt prime. So if you equate this scenario to this equation, so then you would follow that what would follow that your exponential of this Floquet Hamiltonian thing would be equal to your unitary time evolution operator, so that t comma 0, and should be follows the time ordered exponential I over h bar integral 0 to 2 t h t prime dt prime. So that's it. So if there is no drive, so for the case of uh, no drive, that your equation should uh, comes back into your original Hamiltonian. That means that ut of 0 is basically your Floquet Hamiltonian thing, because there is no drive, it doesn't matter, it does not harm anything, and which is also equal to t over h bar. So you can write this capital T. So that's the game. So now you can think of the how the tortorations are made. So I just discuss it in a minute. That so how the time ordered things are there. So basically I just write. So it's a basic principle of time dependent system and how it follows the evolution with time. So that's the game of the thing. So as we know that your psi t is basically u t comma 0 of psi 0. So if you do the trotterization, that means you take a time step, that is the delta t. So you could find out that, so I can just write where u of j, so basically evolution at the jth position, that should be u of tj minus 1 plus delta t. So delta t, your the time step with tj minus 1, and where delta t is basically t over n. So this thing is known as the trotterization, or you can just make a evolution of a system stroboscopically. So it's a basically trotterization. So what we find, so basically we just set up or choose this delta t in a n step in such a way that our original Hamiltonian at that time step should be equal to your original Hamiltonian. So it also can be written as something h t plus something 2 delta t over 2. So this is the case. So you have to choose this time step in such a way that your Hamiltonian at time delta t would be the same with your original Hamiltonian. So what we follow, that if your delta t is much smaller, then what we find that we can write your psi of t is basically e to the power minus I over h bar h of tn delta t, and if you do this for the case of t1, then you would find I over h bar h of t1 delta t of size 0, then as your delta t is very small, so then you just write it as in the integral form, that is the time ordered exponential of minus I 0 to t h of t prime dt prime. So that's the case, and of course there are size 0. So how the totalization are made and how our assumptions are followed, so that's the story. So and also we have to mention that that in quantum mechanics it is just keeping this mind that your h of t1 and your h of t2 do not commute. So I just write it as, because if we take that our example Hamiltonian, that is a sigma z cos omega t plus sigma x, if you do that at t1, that is your ht1, and do this t2, so that commutation of these two Hamiltonian would not commute. You would find out maybe some cos of t1 minus t2 and something. So that's why it does not commute. So it is the signature of our the quantum mechanics or time dependent quantum mechanics system. So you can find out this kind of story. Okay, so now what we do, so it's a very long story short, that if our delta t is very small, so that means it would not harm our original Hamiltonian after a evolution of delta t or the delta t state. So what would happen? So that is very interesting. That means our if our driving frequency is very high, then it leads to our leads to expand our exponential. So that means, as in our problem, that t comma 0, that or the periodic evolution that gives us the e to the power minus I, our time independent Floquet Hamiltonian at time t over h bar, and which maybe as the delta t is very small, so we can just write down in a integral form that I of h bar 0 to t, or maybe the full period t prime dt prime. Then if our assumption is that assumption is t is very small, so that means our driving frequency omega d is very high. So in a high frequency range, we can expand this exponential. So that is known as the Magnus expansion. Magnus expansion at t or maybe inverse of our frequency. So we should do this kind of expansion when our period is very small. That means our driving frequency is very high. Okay, so our left hand side would suggest that our HF should be sum of HFN, and so HF over T over H bar would give you 1 minus I over H bar H of N over T and some higher order terms. So we know the structure of the higher order, but let's focus onto the first order term. So, and for the case from the RHS, so it's a left hand side, and from the RHS we just find out that as our U time evolution to do this quantum dynamics, it's a evident thing, that's Un times Un minus 1 U1, and which suggests you that something Uj uh, so which suggests actually Uj is in the jth position, that 1 minus I over h bar Aj over at delta t, and higher order terms would be there, and which as the delta t is very small, that we can write out, right, we can, it can be written that I over h bar 0 to t dt of h of t and higher order terms. So immediately our Floquet assumption and the dynamics of the quantum mechanics, just equate the or compare the uh, both of the procedure, and find I just want to find that how the this HF, this Floquet Hamiltonian look like, or uh, how it is being done to find out this HF. That's the Gustav Floquet did in his differential equation, that he want to find out that mu, which is the unknown coefficient, comes out from the periodic differential equation. So in this scenario, that we have to uh, find out the structure of the Floquet Hamiltonian. So that's why we did it perturbatively, because as it's a the time steps are taken very small, and so or the time steps are taken in such a way that our original Hamiltonian will be intact in its original form, and as it is a periodically driven, that means it also preserved its original structure at that period. So it the Hamiltonian show or replicate itself or repetitively at that period of time. So that's why we can generalize this formula, that when this high in the high frequency regime, that when the time so periodic time or is very small, the time period is very small and the driving frequency is very high, and if our time steps, that's the delta t, is very small, we can expand the exponential and equate the exponential up to the first order term. So that's the goal, because I know the higher order structure of this expansion, but we don't need to focus right now. So let's focus in this first order form. So if we do this, so we can perturbatively find out from this Magnus exponential how the HF, that's the Floquet Hamiltonian, look like. So that's the goal. So I just erase it, and from here I just followed a structure that is very interesting. That is our h of f at first order term, that is basically 1 by t 0 to t h of t prime dt prime, or if you just do it in some sort of a z basis, so just taking z t prime over t, that 0 to 1, so z, so it is no longer there dz. So what we find out that in the high frequency limit, the first order of my Floquet Hamiltonian is basically the average of the original Hamiltonian. So, or the time average of the original Hamiltonian. So that's very interesting that when we do the perturbation, that first order terms gives you the local term, or maybe that we just we did in our this program, that the Bose-Howard model. So we just perturbatively increase uh, or perturbatively go through some sort of the regime. So there also we just encourage ourselves or appreciate ourselves that the first order term is basically a mean field. So like that way, in the periodically driven system, the first order term of the Magnus expansion is basically a average of the or the time average of the original Hamiltonian that it's followed. So that is the case. And if you want to do the second order, so that is also can be write out that one. So it's here is a 1 by t would be there. So 0 to t dt1, 0 to t1 dt2, that h at t1, h of t2. So this is a second order. So if you go for the higher order scenario, then you just find out the nested the nested commutations, and which would be a complication, which is very tedious, but technically it is very trivial to solve. But that computation, that's computation of this nested commutation, if you go to the higher order, then that is very much complicated in the form of the thing. So that is the case. So that's how you can find out that your Hn of f, and it is not necessary to do that, because in the perturbation theory, it is necessary to know the first order and the second order term up to the that limit, because we, in the case of the perturbation, most of the theories that uh, most of the theory gives us some ambiguity in it, because all the perturbation, if you want to know the convergence of the perturbative expansion, we don't have any answer, because people don't have any answer, because it's kind of that's why we do perturbation. So the you would not ask any kind of question to a physicist that the convergence of the perturbative expansion. So we just do this because we don't know exact answer. So, and it's an open problem for the case of the convergence of the Magnus expansion. So if you are interested to uh, think in deep, then you could, but the whole scenario of the periodically driven system, and then how it behaves and how to solve this kind of a periodically driven system in quantum mechanics using the Floquet theory, that's the story I ended up. So I think it's a good point to stop to uh, digest for you to understand this Floquet theory. And I think it is very trivial thing, and not so very trivial. So it's not trivial. So it's trivial in its form, but it is not so trivial in the description of physics. So in the research nowadays, people do this kind of Floquet problem, that a periodically driven system or the periodically driven nonlinear system. So the technique they would follow, that's the fundamentally, that is it. So it's done. So okay, so that's it. Thank you.